Good morning. Today we're going to talk about section 7.3 in Math 111. And section 7.3 is entitled Simplifying Radical, almost said rational, Simplifying Radical Expressions. Alright, as we may recall, section 7.1, we really defined and simplified some very simple radical type expressions. And we're going to go on to talk about some slightly more difficult situations here that might arise. Refresh our memories in section 7.1. Well, we know that the square root of 25 is 5, right? Why? Because 5 squared is 25. In other words, 5 is the number I square to get 25. So, when we're taking the square root, we're really doing the reverse or the inverse of the squaring operation. Square root of 100. Well, we know the square root of 100 is 10, of course, because 10 squared is 100. 10 is the number I square to get 100. Alright, nothing new here. How about the square root of 50? Well, how are we going to simplify the square root of 50? You might see this on an exam with this instruction. Simplify the square root of 50. Well, 50 is not a perfect square, meaning it's not the square of an integer, right? If you go through the first few integers and square them, you'll see 50 is not going to be on the list. Alright, so the square root of 50 is not going to be an integer value like 5 and 10 were. Well, what can we do here to simplify this expression? Well, I think we can see the square root of 50 I can rewrite as the square root of 25 times 2. Now, as you may have noticed in previous classes, we've kind of hinted at this, you can distribute a root sign over a product. So in other words, the root of a product is really the product of the individual roots, and of course the square root of 25, I can simplify that. The square root of 25 is 5, and the square root of 2, well, the square root of 2 can't be simplified any further. So my final answer would be 5 times the square root of 2, or some might say 5 root 2. Alright, so this is what simplifying radical expressions is all about, identifying perfect powers inside of a radicand, which I can hopefully get out from under that radicand statement. The square root of 12. Well, 12 is not a perfect square, but 4 is a perfect square, and 4 is a factor of 12. Of course, I can write the square root of 12 as the square root of 4 times 3, and then break up my root over that product radicand. And of course, the square root of 4 simplifies to 2, so I'd have 2 times the square root of 3, or more formally, 2 root 3 would be my completely simplified answer here. This answer is what I call in simplified radical form or simplified root form. Well, basically that means you've taken out everything from under the root sign that you can, according to my rules for roots. How about the square root of 98? Well, I think you'll recognize 98 is not a perfect square. 100 is, but 98 is not 100. Well, I can recognize 98. Hopefully I can recognize 98 as 49 times 2. And breaking up that root sign over that product, I see 49 is a perfect square and simplifies. The square root of 49 is 7, of course. 7 times the square root of 2. Simplified radical form when you've taken out everything you can from under the root sign. Alright, not all roots are square roots. Let's talk about some cube roots here. Well, what about the cube root of 54? If I ask us to simplify the third root or cube root of 54? Well, if I look at perfect third powers, I see 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, and we're too big. We're beyond the 54 we're looking for, so clearly the cube root of 54 is not going to be an integer, right? 54 is not a perfect third power. Alright, well, what I can do, hopefully, is recognize, well, 54 is not a perfect third power, is not a perfect cube, but it contains a factor of 27, which is a perfect cube, right? So I can rewrite that radicand as 27 times 2, and as we've seen today and in earlier sections, you can break up a root sign, or distribute, if you like, a root sign over a product. Alright, so now we have the third root of 27 times the third root of 2. Of course, the third root, the cube root of 27 is 3 times the cube root of 2. I can't go any further than this. You're completely simplified when there are no factors of 2 that are a power of your index or greater. So this would be my final answer, 3 times the third root or cube root of 2. Let me rewrite that, 3 times the cube root of 2. Alright, that's a third power, or simplifying a third root. Let's see if we've got a fourth root here. What's the fourth root of 48? Well, let's investigate some fourth powers. 1 to the fourth is 1. 2 to the fourth is 16. 3 to the fourth is 81. So 81 is bigger than 48, so 3 is going to be too big. Well, 48 is not a perfect fourth power, but I think it contains a factor of 16, does it not? So I can rewrite 48 as 16 times 3. I believe that's correct, right? 3 times 16 is 48. Yes, all right, 3 times 6, yeah, 30, 3 times 6, 18, carry the 1, 3, 9, 3 times 3 is 4, yes. All right, so I can then distribute, did you spot that mistake? That should be a fourth root, 4 in that index. All right, so the fourth root of 16, well, let me be a little formal here. Slow down a little bit. All right, so I can break up that root over that product. In general, I can always break up a root, no matter the index, no matter the radicand, barring any sign difficulties. I can always say the nth root of xy is always the nth root of x times the nth root of y. And I can use that property to simplify roots of this type. What's the fourth root of 16? Well, the fourth root of 16 is 2, is it not? Because 2 to the fourth power is 16. And the fourth root of 3, well, 3, that's as simple as I can get. There's nothing left here in my radicand that's a perfect fourth power of anything. So my final answer, 2 times the fourth root of 3. On your test papers, please be sure to clearly indicate your index. Not all indexes are 2. Not all roots are square roots. Alright, we've done a bunch of example up to some fourth roots of simplifying root type expressions involving numbers only. What I want to do is look at some variables now, and what I want to note here is I'm going to assume all variables are greater than 0 in this section, so we don't have to mess with absolute value symbols if necessary when my indexes are even. Alright, so we'll assume all variables are positive values, and let's investigate something like this. Simplify, well, let's start nice and easy, the square root of x cubed. Well, clearly x cubed is not a perfect square. Remember, when no index is specified, we are assuming a square root, or 2 in the index. Alright, x cubed is not a perfect square. There's no quantity of x with an integer exponent anyway that I can square to get x cubed. Well, what I can do is say x cubed is not a perfect square, but x squared is, right? So I'll break up x cubed as x squared times x, and again I can break up that square root symbol over that product. The square root of x squared, of course, is x times then the square root of x. Alright, so my final answer here would be x times the square root of x, or some might say x root x. Again, this is simplified root form, or simplified radical form. And informally, that means you've gotten everything out from under that root sign that you possibly can. Alright, let's make a new screen. Alright, let me adjust things, hang on. Alright, there we go. Simplify. The square root of m to the 9th power. Well, if my index is 2, and it is, and I've got an odd exponent on m inside that root symbol, it's pretty clear I'm not going to be able to take out all these powers of m out from under that root sign, but I can take 8 of them out, right? I can break up m to the 9th as m to the 8th times m. Why am I doing that? Because I can take out as many powers of m that are multiples of my index. Notice 8 now is a multiple of 2, so I can then break up that root sign over that product in the radicand and say the square root of m to the 9th is equal to the square root of m to the 8th times the square root of m. Alright, what's the square root of m to the 8th? Well, of course, that's m to the 4th. Why? Because m to the 4th squared is m to the 8th. Alright, now a nice little shortcut here. If you're in this situation, you take your exponent here and divide by your index. 8 over 2 is 4. A little bit of a shortcut. Alright, the square root of m, well, m is stuck inside, right? The exponent on m is less than the index, and when that's true, you're in simplified root form. So let me write this out a little more formally. M to the 4th times the square root of m would be my final answer. M to the 4th root m, some might say. And again, this is simplified root form, or simplified radical form. Okay? Alright, let's do some harder ones here. Simplify. How about the square root of 98b cubed? Well, you might think we're in trouble here. 98 is not a perfect third power, or perfect second power. Again, your index is an invisible 2 here, right? Square root. 98 is not a perfect square. B cubed is not a perfect square, but I think they both contain factors that are perfect squares, right? Of course, 98 is 49 times 2. And I'll put the 2 over here because the 2 is going to stay inside. Similarly, b cubed is going to be b squared times b. You can take out as many powers of a variable that are multiples of the index here. That's 2. Alright, so a 49b squared is going to come outside and a 2b has to stay inside. The square root of 40, oops, it should be a b squared there. Hang on. The square root of 49b squared is, of course, 7b times the square root of 2b. Well, that's as simple as I can get. There are no perfect second powers in that radicand, so I've gone as far as I can. I'll call my final result 7b times the square root of 2b. Final answer. Alright, how about something a little harder? Simplify. the following radical expression. 10 times the square root of 128 a to the 5th power. Alright, so what I'm looking for here, this is a square root, so I'm looking for perfect squares buried inside that radicand of 128a to the 5th. 128 is not a perfect square, but it is a multiple of 64, is it not? Notice that 10 is a factor outside that root operation, so I'll say that under the root sign, 128 is 64 times 2. Basically lining up the factors that are coming out from under the root sign on the left side of the radicand according to my multiplication associative law. A to the 5th is not a perfect second power, but a to the 4th is, right? So I can rewrite a to the 5th as a to the 4th times a. Right? These are perfect seconds powers, or perfect squares. I can say then, I'm going to be very formal here. After a while you skip steps on this. Oops. 4 there. The square root of 64a to the 4th times 2a is equal to the square root of 64a to the 4th times the square root of 2a. Of course, I can simplify this root now. These are perfect square powers under that root sign. 10 times, don't forget about 10, the square root of 64 is 8, and the square root of a to the 4th is a squared, right? The square root of a to the 4th is a squared. Our little hint, you can take this exponent and divide by the index. 4 over 2 is 2, right? Alright, don't forget about the lonely square root of 2a. 2a's got to stay inside. And of course I can clean this up a little bit. 8 times 10 is 80. A squared times the square root of 2a. Final answer. Okay. Square root of 150, simplify. No variables here. The square root of 150. Now you can break up 150 a lot of different ways. Well, again, we're looking for perfect square powers, or perfect second powers, embedded in 150 as a factor. I think we can see 150 is 25 times 6, and I chose that factorization because 25 is a perfect square, and it's the largest perfect square that's a factor of 150. Alright, let me skip a step here. The square root of 25 is 5 times the square root of 6. Well, that's as far as we can go, right? The square root of 6. 6 contains no perfect second powers, so this is my answer in simplified root form. Let's try something a little nastier, something, let's say simplify the third root of 297 times b to the 4th power. Alright, so I've got numbers and variables involved in the root sign and a higher order root, a third root now. Well, the idea here is I'm going to be looking for perfect third powers that are factors of 297 and also b to the 4th. I claim 297, I believe that's 27 times 11. Let me check it. 27 times 11, hang on. 27 times 11 is indeed 297. Alright, so that'll come in handy. 297 is 27 times 11. And of course, you can take out as many powers of your variable that are multiples of your index. So 3 factors of b can come out, and 1 factor b is going to stay inside. I'll now distribute that root sign over the product, and the cube root of 27 is 3, the cube root of b cubed is b, times the third root of the remaining factors, I call residue factors, that have to stay inside the root sign. So 3b times the third root of 11b, final answer. I got 3 more here. How about the fourth root? This one's probably the hardest one of the day. The fourth root of 224 s to the 8th times t to the 7th. Well, you're going to have to look for something here. 224, you're going to look for perfect fourth powers that are embedded as factors into 224. Well, fourth powers, let's look. 1 to the 4th is 1. 2 to the 4th is 16. 3 to the 4th is 81. I believe 224 is divisible by 16. Let me check it. 224 divided by 16 is 14. Yes, it is. So I'm going to break up 224 as 16 times 14, right? Now 14 is not a perfect square. 14 is 2 times 7, so it's going to stay inside. S to the 8th. Remember, you can take out all 8 powers because 8 is a multiple of 4. So s to the 8th I'll pile up on the left here. T to the 7th. Well, 7 is not a multiple of 4, so I can pull out 4 t's, but 3 t's are going to have to stay inside. Alright. I can now rewrite this as the fourth root of 16 s to the 8th t to the 4th times the fourth root of 14t cubed. Alright, I'll go through here and take the fourth root of each of these perfect fourth powers. The fourth root of 16 is 2. The fourth root of s to the 8th is s squared. The fourth root of t to the 4th, that's just t, right? So I'll get 2s squared t times the fourth root of 14t cubed. And that's my final answer. I've completely simplified as much as I can. I got everything out from under that root sign that I could. 2 more. Let me get a fresh screen. About simplify. The square root of 200 x squared y. And let's see, I'm looking for perfect squares here under that root sign. Well, 200 is not a perfect square, but 100 is, and I claim 200 is 100 times 2. What about the variables? X squared, well, I can take out both powers of x because 2 is a multiple of 2. And one factor of y has got to stay inside. So I can say, well, let me skip a step here. The square root of 100 is 10. The square root of x squared is, of course, x, assuming variables are positive, which we are. And the square root of 2y has to stay inside under the root sign. 10x square root of 2y. Last one. The fifth root of 243 r to the 22nd. Simplify. Now you start getting to these higher order index roots, and sometimes it's a little difficult to find, for example, in this case, perfect fifth powers that are buried in these rather large numbers. But I think 3 to the 5th power is 243. Well, let's check it. 1 to the 5th is 1, of course. 2 to the 5th is 32. And 3 to the 5th power, well, that's going to be 3 times 3 times 3 times 3 times 3. Let me check it. 3 to the 5th power is indeed 243. So we kind of lucked out here. Alright, so all of this 243 is going to come out from under the root sign. What's going to stay inside? Well, again, you can take out as many powers of r here that are multiples of your index. Well, 20 is the highest multiple of 2, less a multiple of 5, less than 22. So 20 factors of r, 20 powers of r can come out from under the root sign. Let me rewrite this. 243, all of that's coming out. 20 factors of r can come out, and that means 2 factors of r got to stay inside. Alright, the fifth root of 243, well, we already established that's 3 because 3 to the fifth is 243. The fifth root of r to the 20th, again, you can take your exponent and divide by the index. 20 over 5 is 4, so 3r to the 4th. And the fifth root of r squared, that's got to stay inside the fifth root of r squared. Okay, you're in completely simplified form when you've got no constants that are perfect powers of your index, and similarly your variables have to have all the exponents less than the index. Instead, 2 here is less than 5. So there's my final answer, 3r to the 4th times the fifth root of r squared. Alright, we'll call it a day. This concludes section 7.3, Simplifying Radical Expressions.